Here we are in the National Museum of Automobile in Mulhouse, and we have about 600 cars. All these cars were gathered from two brothers, Hans and Fritz Schlumpf, in the 60s. And the collection is national for 40 years now. This is a Bugatti Type 30, and on this car we have a big trouble on the cooling system.
Okay.
I can show you.
Okay, but you have the same problem on all of them, most of them.
Most of the Bugatti we have.
Okay, so it's a representative one.
Yes, exactly. So the principal degradation is here, you can see. Okay. So here you can see we have two examples of parts with corrosion.
Okay, so part of the metal is fully missing.
Yes.
So what is the risk that eventually, because you have a durite on top?
Yes.
So what might happen is that the cooling solution might not play its role anymore.
Yes.
Because it's not anymore sealed.
Yes, you can have a big leak, and it would be very damageable for the car.
Okay. We are going now to analyze this metal. So which one is it? This one? Okay.
Yes, this piece.
Good. To analyze it, we need to have a voltmeter, which you have here, and the measuring system. It's a reference electrode, so it has a potential determined. And when you measure the difference between the two, then you have the potential of your metal. And so what we have to do now is to approach this measuring system to the metal surface, but first we have to prepare the metal surface. It's better if you do it, because you are a conservator and you know how far you have to go, but you have to insist a little bit. It's not only a slight pressure, a bit pressure, but be careful to be very localized. So you can take this. Because it's enough, it's fine.
I think it's okay.
Then you approach the reference electrode next to the metal surface, but you leave a distance of a few millimeters between the surface of the metal and the tip of the reference electrode. Okay. Just a few millimeters. Okay. And then you insert a certain volume of solution between the metal surface and the reference electrode, and thanks to that solution we'll get a measurement. So be careful to not spread the solution. It has to be just between the metal and the reference electrode. Okay?
Okay.
And you just have to click on the scanning of the potential and we are done. Okay, so it's fine. So now we are going to continue that during 5 minutes, 2 times to check that the measurement is correct. But 5 minutes is not enough. You have to do it during 15 minutes. And the 15 minutes measurement, in fact, will be the one we will use later on for the analysis. And you will have to repeat that with the 3 solutions. So once that will be done, we will process the data. Okay? So I'll leave you doing it, because now that you have the process, you can do it by yourself. Okay?
Okay, thank you.
Okay, so I can see that you obtain your plots now in this solution. You see that the values are not exactly the same, but the trend is always the same, and it's good that the plot for 15 minutes is within the range of the others. Now I check with the other solution, the same, so for me it's perfect. And last one, the trend is slightly different, but it's normal for aluminum alloys. Again, the other plots for 5 minutes are quite similar. It's good. You kept the one of 15 minutes. So now you have your 3 plots in 15 minutes. You have to highlight them And you will create your material, so you have to go to test, and that will create your electrochemical behavior of your metal in the 3 solution. We had not reproducible results, so you have to click here on these characteristics, and then you accept. Okay, so now you have your metal characterized electrochemically, and you have to compare this one, so you have to highlight it and compare it to the library, which you have there. If you click on library, okay, and go back to test.
It's highlighted?
Yeah. Okay. Go to test and click on match. So now you have the comparison of your plots for your metal to all the alloys of the databases. And you have to see which graph is similar to the one of the database. So now you would have to move, if you move the cursor here, you will see that the plots are different, it's normal, because you have a look at all the database. And what we are looking at are plots which are very close to one another. When they are close, it means that you have a good chance to have a metal close to the one of the database. So now if you go to proposal, and you highlight the 10 first, you see that in the list, the first alloys proposed by the system, which gives the best comparison, contain copper. So it seems to indicate that your metal contains both aluminum and copper, and that is a problem, because we know that aluminum copper alloys are not very resistant to corrosion, and it could be that the cooling solution will eventually corrode your metal. So now you have to see what is the best for you. This tool is just giving you not an exact composition, but it tells you that your metal is an aluminum copper alloy.